Let's do a sound check before. All right. Oh, I should. Okay, so this seems like fine sound quality. It's not amazing because there's background noise, but it's fine. And sound quality. It's not alright. Yeah, this is way better than last time. Hello everyone, welcome to the Mesh Optimizer stream. That's not really about Mesh Optimizer, but hey, we'll be solving a problem in Mesh Optimizer. I will be just mostly not talking about Mesh Optimizer per se. Hopefully the sound works better than it did last time. I figured out what was going on after the stream. Like, I wanted to fix this, and I was kind of going crazy, like trying to change the settings, and I tried to use a different mic and it still was bad. And then I noticed that there were like two lines in this mic aux thing, and I thought before that this is like stereo input from the same microphone. Apparently it was capturing from two different microphones, so the results were really weird. And this time we are not making the same mistake because we are using just one microphone, the right microphone. So here's what we are doing today. We are solving a specific problem, and in the course of solving this problem I very briefly looked into this problem before, and I kind of know the general shape of the problem, but I don't really know all the details. But the problem is manifesting as follows. So this is my test program that like does the simplification and whatnot, and you know, you can run it in the release. And let's see, okay, cool. And let me run it again because it was compiling it. So I run it, there's immediately some output on the screen, and then it takes like a split second to show the window. And that's a bit of a separate problem that's not even in my code as far as I remember. But the text appears on screen instantly, right? So it's hard to tell how long it takes, but it's not really perceptible. Now, in the release build, the assertions are disabled, it's harder to debug code, it takes longer to compile code, so it's more comfortable to work in debug mode. Here's what happens in debug mode. Let's do this again. Right, so there's visible delay that seems to be more than a second, maybe like a second and a half or something like this. From the point the console window appears till there is the first text that's displayed. And okay, you can say, hey, it makes sense. It's a debug build should be slower because optimizations that the compiler does are not enabled. But if the debug build is slow enough to be annoying or unworkable, and in this case it's still workable, but it kind of annoys me. And the file that we are loading right now is not very large, so let's look at this. So this is this beautiful file. So this is 3 megabyte file, 3 megabyte mesh file that I'm loading. And you know, it's like sort of large, but there's way larger files. Here's another file that's substantially larger that I test my code on. This is 93 megabytes, oh my god, okay. 1, 2, 3, 4, 5, 6, 7. This is like an eternity, right? So this is not workable. The other file is annoying, this file is just not workable. And you can say, hey, this is a large file. I don't even know how long it will take. This is insane. Okay, this is worse than I thought it would be. Come on. All right, let's not wait for it because it's too long. But in release, right? So it takes like maybe a second and a half before the screen, before the text first appears. So in the release it's fine, in debug it's really not fine, and then if I use a smaller file, then in debug it's annoying, right? And I don't want the code that I'm working on to be annoying. So let's do the sensible thing and figure out why our code is running slow. Let me check. All right, nobody says that sound is broken, which hopefully means that the sound is not broken this time. So the way we do this is we use the built-in Visual Studio Profiler and just run our code. You can see that it says solution configuration set to debug. Switch to release configuration for more accurate results. So this is a great warning, by the way, because the number of times that people run debug builds assuming that these are release builds and then they are really slow and then they measure performance on these, this happens very frequently, right? So it's nice that Visual Studio displays a warning. Profiling and debug is not a common operation necessarily, but it's nice to have your code run quickly in debug because it makes iteration times faster. This means I'm changing something, I have this large mesh, right? I changed something and I want to quickly see if it works. Should I switch to a small mesh? I could switch to a small mesh, but if large meshes work well, then this is fine. Like I could use a large one, right? And then maybe there's an assertion that happens on a large mesh. And I could try to replicate this problem on a smaller mesh, but once again, if the debug builds are fast enough, I don't have to do this necessarily. So there's a lot of reasons why you might want your debug builds to be fast. And fast doesn't mean you are good with shipping them, right? So if your game runs at like 60 frames per second, right? I mean, if your debug build also runs at 60 frames per second, this is amazing. This means you're not, like your bottlenecks are elsewhere. If your debug build runs at like 20-30 frames per second, this is still very, very workable, right? You can run the game, you can play the game, you can go through levels. It's not an amazing experience, but it's very playable. If your debug build runs at like 2 frames per second, this means you are not using your debug build day to day because it's just too painful. So this is not a great place to be in. And if this happens, you might want to start profiling your debug builds, which is what we'll do right now. So now we are only really interested in this first phase where it kind of loads the mesh right now. But let's just look at the entire profile just to see what it looks like, right? All right. So there's like multiple ways how you can look at the profile. Let's just look first at the top-down profile. So the number of samples here, by the way, is the same as the number of milliseconds spent in this code, because by default this profiler is configured to do 1,000 samples per second. So it samples at kilohertz. So this is convenient because the number of samples that you see here directly corresponds to the millisecond time. And these numbers aren't stable run to run, right? If I run this again, then maybe I will see a slightly different number here. And I would expect the deviation to be like a few percent, 5% worst case maybe. And there will be outliers, so I guess worst case you can see way larger deviation. But in general, I will not be too scientific about this because the problems here are not, oh hey, debug code runs 10% slower than I'd like it to run. No, debug code runs really slow here. So let's try to figure out what's going on. And so immediately we see this interesting problem where all of the time during this loading process, or most of the time anyway, is consumed by the parse OBJ function. And so let's very briefly look at some other stuff. So there's this optimize function. And the optimize function isn't generating an OD yet. But, oh, actually, let's do this. So right now when I run this code, let's do another profile. This will be fun. So what happens when I run the program right now is it opens the mesh, opens the window, and draws the mesh once, hopefully. Maybe twice, but it tries to not draw the mesh if nothing changes. If I press 9, and I will do this right now, it will simplify the mesh once, right? Right, so it simplified the mesh, it thinks it took it like 150 milliseconds, and then it had to draw the mesh again. So let's close this. So the reason why I wanted to do this is because now I'm looking at an optimized run that actually did work, right? So like in the previous run, we didn't really optimize the mesh. Now we did run our optimization code, all of the code that we wrote last stream, all of the code that I wrote before that. It has to go through the vertices, it has to do vertex classification, edge loop detection, multiple passes of collapsing edges, compute error factors for edges, sort edges by the error factor. Like, it has to do a lot of work, right? Now, parsing an OBJ file is also not super pleasant, and it's not like it's no work at all, but it doesn't seem like parsing an OBJ file should be that much slower than running a full-fledged simplifier. If we look at our code tree now, then we can see, hopefully, let's see. So this extra optimize run didn't really change our stats much, right? And we can check that it actually goes. Does it go through all of the? Is this the same? This is oh, right. Yeah, so the second optimize run is like here somewhere. Hold on, right. Okay, yeah, like the problem is the second optimize run happens when I press 9, which invokes GLFW, which is the framework I'm using for creating the window and stuff. Handler, so this is where the second call goes. Okay, so it took us by the count of profile. Oh, and the 147 milliseconds I was mentioning there, this was like wall clock time that included printing to console, and printing to console was slow. So I think it's probably reasonably fair to say that it took us around 80 milliseconds of CPU time, give or take, and I could disable debug prints, but around 80 milliseconds to optimize the mesh, right? In debug mode, no optimizations whatsoever. And then it took us like 47 milliseconds to do the first run through the optimize function before we actually pressed 9, which does like half the work, because it basically looks at the mesh, figures out a bunch of stuff, and then says, oh wait, there's like nothing really to optimize because I'm already at the number of triangles that I want to have. And I will maybe optimize this at some point to make it just instantly return, but whatever. Alright, so 80 milliseconds in debug mode to optimize the mesh. 140 milliseconds to display the mesh using OpenGL, which is, there's also some problems here that we'll talk about. So then it took us 250 milliseconds, oh wait, actually this is not quite true, like 120 milliseconds, let's say, to initialize this library. And this is also not great. I looked at this, like if you look at this code, it spends half the time enumerating joysticks. And like I don't have a joystick or a gamepad or whatever plugged in. So I don't know what this code is doing. And I actually fixed, so this is not my first encounter with GLFW. There was a problem like this. Let's see if GitHub still remembers. Or actually, this was a pull request. Yeah, so you can see I contributed a few, like a few changes to GLFW, and curiously, you can see that I had to solve a problem like this on Mac. On Mac, I used to use a Mac. Now I use a Windows laptop, and so this init joysticks function was like really slow, and really slow means I don't remember. Like by my standards, it was really slow. Let's see. Right. So with external keyboard and mouse attached, it took like 300 milliseconds. So this means every time I ran my code, there's an extra delay before I can see the results. And it also bothered me, and I decided to fix it, and then I fixed it. And I actually had to buy a gamepad for this because I did not have a gamepad, and it's hard to test the code that optimizes gamepad initialization without having a gamepad. Anyway. So I had to fix a problem like this on Mac. I'm not sure what the problem is on Windows, so I don't know if I will be able to fix it or if it's just, you know, a given. And the fact that this is using direct input is not great, but there's like no other way to do, or there are other ways, but there are no other good ways, nice ways to do general gamepad input if you want to support like all devices on Windows. So, okay, so this is not awesome. But this is like 120 milliseconds. And so there's this beautiful parse obj function that takes 1200 milliseconds. So this is what takes this second and a bit. And we can look at this code, and we see a surprising amount of functions that start with std::. And this is the standard library. And this is what we are talking about today. So specifically, meshoptimizer library does not use STL at all. And the reason is I want it to be as fast as possible. I want it to be as quick to compile as possible. I want people to be able to use my library regardless of their preferences, and a lot of people do not use STL and they will refuse to use libraries that use STL, and there are some good reasons for this. So my library doesn't use STL. However, the object file parser, the OBJ file parser, which parses this mesh file, does use STL. I wrote it before I removed all of the usages of STL from the core library, and I just didn't think it would matter that much. I mean, this code loads OBJ files. How slow can it be? Well, turns out it can be slow, because the reason I had to write my own OBJ parser is because the default library that you would use, OBJ, tiny OBJ loader, it was like slow in the sense that whenever I would profile my code, I would see the OBJ library take a lot of time, and then all of my optimization routines take less time. And this also bothered me, and I just wrote my own. And it's not that much code to parse OBJ, you know. So there's like 400 lines of. Oh wait, this is not this is not the right file. It's also 400 lines. So there's like 400 lines of code here, right? Like 350. So it's not that much code. It's relatively simple code. Half of this code is functions to parse integers and floats that I just wrote some time ago. They work, they're fast. They're not, they can be precise, but this variant is not super precise, as the comment indicates, but these work well. So they serve me well. I tend to copy them around the code that I'm writing whenever I need, like whenever float parsing becomes a problem and I need to fix the problem. So half of this code is, I guess, like a third to a half is parsing floats and ints, and then the rest is just, hey, let's go through the object file, let's parse it. And this is not, there's nothing super stupid about this code, right? This is not like super smart code, but it's not super stupid code. And so this code is slow. So why is this code slow? So this code uses vector. So it uses standard vector container. For people who don't know C++, this is a dynamic array that you can resize, that you can add elements to, etc., etc. And one of the functions we use is pushback, which says, hey, let me add a value to the end of the container. Now, so here's our problem, right? So our problem is OBJ parsing is slow. Or rather, it's slow in debug, it's pretty fast in release. So just as a point of comparison, let me run the code, not the graphical program, but just my test suite in Linux. So this is a Linux, it's not a VM, but this is like Linux on Windows. This is Linux subsystem for Windows, which I love, which is amazing. I use it every day. It sort of made me, the only thing that I really liked about macOS is how close the Unix terminal was to the rest of the system. And I like working in the Unix terminal for a number of reasons, and I'm kind of used to that. So it was really convenient for me to just go to the terminal and do something. And then Windows has this arcane CMD shell with DOS commands, and there's PowerShell, which is like simultaneously worse and better. And this is just not a good environment for me to work in. And so this is a feature that's new in Windows 10. This is Ubuntu. It should say somewhere. Oh, right, yeah. Okay, wait. Come on. There's some way to print this. Aha! This is Ubuntu 18.04. It's running on Windows. It's going through the Linux kernel and then through the Windows kernel, sort of. Or maybe there's no Linux kernel. I forgot how it works. Oh yeah, right. I think there's no Linux kernel here. There's just a Windows thing that sort of pretends like it's a Linux kernel. Most of the code works here. There's some performance issues with I/O. File access is kind of slow. I think Microsoft is working on this, but it requires like deeper changes in Windows kernel. But this is like, I like this. And the nice thing about this is CPU performance is exactly the same. It's just running native code. And it's really, really easy to work with this. And as you can see, it automatically mounts my NTFS drive into Linux. So I don't even have to worry about files, where do they go, it just works. So this is nice. Anyway, So what we can do is we can run, let's compile our code. Alright, nice. And let's run it with the file that we were using. And this is running in release mode right now. This is because this is just a default. The reason why the default config here is release is because I basically never debug in this view, but I work on performance a lot in this view. So all of these like timing printouts, right, are for me to try to improve performance of the code that I'm writing. So release is a nicer option, but this is a release build with assertions enabled. So it's technically slightly slower than a full release build, but not by much. Anyway, this is the code, roughly speaking, right? It's not one-to-one. This is not a super fair comparison because technically this code is different from the OBJ loader is the same, but we are running this parse OBJ function. And I think there might have been a small difference between this one and the other one. But maybe that's not true. Let's see. Actually, these functions look the same to me. Okay, it's probably the same code. I mean, this function isn't shared because all of these are demo programs, right? So there's no point like making a reusable function that loads an OBJ file into a vertex format of your choice. So the reusable library, come on, looks like this. So you can load a file, an OBJ file from a path, or you can load it yourself line by line if you just wanted to feed data from like HTTP stream or something to it. It mirrors one-to-one the way how OBJ files store information. I will not go into how that works exactly. Suffice it to say, basically there are several large arrays of data that store vertex coordinates, texture coordinates, normal data and index data and polygon sizes, right? And then you can check if the file that you have is actually looks like legitimately valid file. And I think this was done to simplify the error handling somewhere. I forgot why validate is separate, but it made sense at the time. And also when you wrote an OBJ file, it could have polygons that are not triangles. There's the helper function to triangulate it, right? And this is the code that we are running. So this, hold on. So if you look at this line, what it says read in 13 milliseconds and indexed in 0.8. So read refers to parsing of the file and triangulation. Indexed refers to the fact that we have to process the OBJ file a bit to be able to actually use this because the data that's there isn't really laid out correctly. So this is the release build. All right, let's compile and run a debug build. This is I'm trying to not like overload my system too much, so maybe we'll just build in single. All right, this was like a full rebuild of the library on one core, so it's not too bad. Anyway, so we can see here that indexing takes like 3.5 milliseconds, which is quite a bit slower. Is this the right file? This is not even the right file. Wait, what am I? Hold on. How? Oh, interesting. Wait. Why? Oh, files. Oh, wait. All right. Please disregard all of the timings that I was just saying. The file is wrong. Let's do this again. So debug build, and then release build. All right. So yeah. Okay. So that makes more sense. So in debug build, it takes us 40 milliseconds to load the file and 14 to like fix it up. And in the release build, it takes 22 and 7. So the release build here is like twice as fast as debug, which is a really nice threshold. I mean, I'm pretty happy if debug build is just twice as slow. This means if your game ran at 60 FPS, it will run at 30. So this is nice. This is not what we see in Visual Studio, however, and the reason for this is there's multiple reasons, right? So first, Visual Studio is not using the same compiler. So this is using GCC, and Visual Studio obviously uses their own compiler. And the second reason is the implementation of the system library, or rather the standard template library, is different. So all of these containers, vectors, the interface is exactly the same, but the implementation is very, very different. And so if in Visual Studio I was getting these results, this stream would not have happened, right? Because these are great results. I have no issue with this. And this code is perfectly debuggable. I mean, if you had like a graphics debugger, but okay, let's do. Alright, so let's debug this just to prove that, hey, debugging works. And I know that this is GDB, which is a console debugger. Here's the thing that many people don't know. If I press Ctrl-Alt-T, or maybe not, Ctrl-Alt something, but basically it's to enable, I think, then GDB actually has a GUI built into GDB. It's text mode, so it's, you know, a bit junky possibly, but it's actually nice. I use this from time to time whenever I sometimes just don't run Visual Studio and just debug in this thing, right? But so let's put a breakpoint into something, I don't know, like let's put a breakpoint here, right? So this is line 140. And let's run our program, and you can see it breaks at V. We can print the value V, we have the values, we can print VI, VTI, VNI, we can then print file V, which is this vector. So you can, this is a function debugger, right? So it's not like there is substantial functionality missing here. Things work, right? But in Visual Studio, things also work, but things are slow. So the question is, why are things slow in Visual Studio? And the answer is between the compiler in debug mode and the standard vector implementation, the result is slow. So if you look at OBJ parse line, which takes half of this function, then you can see that out of 600 milliseconds spent in this function, we are spending 300 milliseconds adding data to a vector of integers, 175 to a vector of floats, 43 to a vector of chars, or cars, or chars. Let's just call them chars. I think the correct abbreviation is car, but I sort of gave up on this a while ago. I tried to use it consistently and then just said, hey, whatever, char. And also 25 milliseconds apparently calling the size function of the float vector. And these add up to, if I can run the calculator, and 43 and 25. So this is like 557 milliseconds out of 622. So almost all of this. So almost all of this overhead is inside std_vector, specifically the pushback function. Now, I always knew that pushback isn't great. There is like a bunch of problems with this. In fact, there was this amazing problem that is now fixed, thankfully. But this problem was there in Visual Studio 2015 and 2017, up until a very recent update, up until 15.7. The current version is 15.8. So it was fixed super recently. As you can see, it was fixed. It's basically mid-May, I think, is when the public release went out. So okay, technically it was fixed like 5 months ago, right? But the problem persisted since Visual Studio 2015. So you could write this function, build it in release for any architecture in Microsoft Visual Studio, and this call will not be inlined. There would be a call to a function in this assembly code, which makes it slower because this function usually doesn't do much work. And this is like measurably slows down some workloads, right, in release. Which is also not an unheard problem. I wanted to share this cool story somehow. Let me. So there's this library called, and so the basic problem, and I'll talk about some problems of STL in a minute, but the basic problem that we are seeing here is different STL implementations just have different performance characteristics, right? Like, this function wasn't inlining in Microsoft Visual Studio for a while. I have never seen this problem up until Visual Studio 2015. And this is surprising, right? So STL is the most used library for C++, probably by a large margin, unless you count the C standard library or the CRT, C runtime, which might be unfair to count, or might be fair to count. But even if it's like the second biggest one, it's still really popular. the fact that this issue persisted throughout 2015 and 2017 for like more than 2 years, I guess, is surprising and shocking, right? So the reason why that specific problem occurred, and this doesn't have much to have with what we are talking today, but I wanted to talk about this briefly to sort of give you an understanding of, hey, writing code is hard, writing fast code is hard, and you have to have a lot of background and a lot of attention to detail whenever you write code like this. And if you don't have this attention to detail, bugs like this happen. And this is not because people who write STL at Microsoft don't know what they're doing. I had good conversations with them, and it's not like they don't know. Things slip, right? But it feels like they don't put enough attention or haven't put enough attention. As far as I understand, things are changing. There might be like more people working on STL now, or I don't know. But basically, based on what I have observed, which is the results, the performance, the quality of the code, it was, in these really common places, surprisingly subpar. So there was this library called STL, which has been touted as this amazing library for like an amazing STL replacement that fixes all of the problems, and Electronic Arts uses this, and Frostbite uses this. And I have, you know, a few bones to pick with that library, but we will not be doing that today. But the basic problem that the Microsoft implementation had is that instead of, if you look at this pushback, you can see there is this if check, and so this is already not great. This code wasn't doing this when I last looked at this, but okay. It says if there's space in the vector, let's just plug the value at the end of the vector, like here, and then increment the pointer. Otherwise, insert the vector at the end. And so what the Microsoft implementation was doing is it had a function like this that was slightly larger than just one function call, like inside an implementation of pushback. And I think this code was maybe a tiny bit more complicated, but maybe not. And so what happened is the function was too big. The function contained the fast path, which is this if and this insertion, and large parts of the slow path, which is this thing. And the compiler said, okay, I look at this function, and it's just a large function. It doesn't know that this is the fast path and this is the slow path. It just looks at the function and says, this function is large. I am too afraid to inline this. So instead, what they do now, which is what STL does and what libc++ does, and what I have recommended them to do on Twitter, and I don't know if they actually have read it, but I'm sure they would have figured it out without my help, is that, well, okay, this delegates to this one, which is, okay, that's like a separate story. Oh my god, okay, alright. So, I think this is the function that we are looking at. I think. Okay. So this is kind of the same code, sorta. It says if we have enough space in the vector, let's insert the element at the end of the vector. Otherwise, let's do this other thing. And the way this code is written right now, the compiler does not inline this call, but it does inline this call and this call. And so this function is relatively simple, and it can be inlined completely in release. So they have fixed the problem, which is nice. There are other things that are tricky when you write STL. So for example, this code, let me see, this code is not super efficient, and here's why. So if we don't have enough space in the vector, we fall back to this generic path. Here's what this generic path is doing. It says, here's a value, and here's the place where to put this value in the vector. But you need to be able to handle reallocation, or rather you need to be able to reallocate the vector, because the vector, like, there's no space for this value, right? And so in theory, you can pass some other place for this than the end. And if you look at this function, we can see that this function does a bunch of setup, and then it says, okay, if the place where I'm inserting the value is the last element, then do something. Otherwise, do something else. Here's what happens. Every time you write pushback in your code, the compiler compiles this function, inlines these bits, usually, and then does not inline this function. Inside this function, you have code that deals with this case that is used in pushback, which is this path. And this path, which will never be called from pushback, but it might be called from something else, right? Like maybe this function is called from something else. I don't know, right? Yeah, it's called from this other function. And so what happens is, turns out, in a large code base, and I was doing this back in the days of FIFA, in a large code base, you have a lot of different vectors with a lot of different types. And for each type, your binary has to contain the implementation of this function that has like half of the function dedicated to the useful bit, which is reallocating and insert an element at the end. And the other half of this function is dedicated to the useless bit, which is if you're inserting in the middle, you have to take the parts of the vector after the insertion point, shift them to the right by one value, and then plug the value in here. So turns out this code just is binary space, and turns out that you could solve like hundreds of kilobytes by doing a change, which is this change, which is my change, but I cannot prove it to you because, you know, I'm sure this GitHub doesn't have the history because this was done in Perforce days and stuff. But this code basically says, okay, the common path in pushback is this one, so this will be inlined. And note how this basically almost doesn't call functions. It calls this function, which is new, but this is like really bare bones. Whereas the Visual Studio version, as you saw, like it calls has unused capacity, and then it calls this guy, and this guy probably calls something, and this guy calls like a billion other functions, and this is two function calls, and this is a function call, 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 and this is insane. But this is what we will talk about in a minute. Anyway, yeah, so basically if you take this function that inserts the value at the end and write a special version of this function that knows that it only handles insertion at the end, which is basically this code, well, on this code, right? There's some path here for people who run with exceptions, but FIFA definitely did not use exceptions. Turns out you save like hundreds of kilobytes of memory. Turns out in a project like FIFA, hundreds of kilobytes of memory are a big deal on a memory constrained platform like PlayStation 3. So the reason I'm explaining all of this is there's a lot of subtlety in STL implementations. It's really easy to get it wrong. You can see that Visual Studio definitely doesn't do this thing that I did in STL. libc++, if I remember right, does do that. Basically, libc++ looks like a high-quality STL implementation to me. Maybe Microsoft should think about supporting. I think they might support libc++ now. Maybe you have to like install it in like some special way, but I think they do at least compile it now, if I remember right. Or maybe they did the other thing. Maybe they compiled their own STL implementation with Clang. Maybe that's what it is. But anyway, so I'm sure if libc++ is not supported by Microsoft, you know, they can fix it. And I'm pretty sure that libc++ is like just a better STL implementation. So if you look at this vector in here, let's look at this pushback. Let's see. Aha, right, yeah. So this is pushback. And you can see this doesn't look exactly like the STL version does. It looks more complicated because it has to conform to the standard a bit more closely than the STL does. There's all of this allocator business that unfortunately has to happen in the conforming implementation. And there are some annotations here that support some debugging code. I forgot what that does exactly. But basically, so this is the same pattern, right? So we check if the end pointer is not like if we have space. If we have space, we do hopefully the minimum amount of work to construct the value. Now this is like more work than necessary potentially because of this stuff, but it's probably close enough, hopefully. And then you have this thing that is here called do insert value end, which, you know, naming is hard, don't blame me. And here is called pushback slow path, which is actually a better name, because this is kind of what the function is for, this is why it exists. Like, it's really easy to look at this code and say, hey, do insert value end seems really weird, because it's just equivalent to this do insert value function if you pass end here. But then you look at this code and this is like twice as big, but it's really natural to say, oh yeah, let me refactor this and like remove this function. No, this function is there for a reason. So yeah, so pushback slow path is a better name. And this does some work, and this is also like not ideal. Like, I don't, what the hell is this? I have no clue. But it looks, it looks more, I don't know, it might be faster. Let's see if we can profile, this code on libc++ just to, so I think right now what happens is when I use GCCs, it uses, oh, we are like 40 minutes in. Maybe I should start looking at the implementation. Alright, yeah, you know what, let's not profile libc++ because this is not the point. The point is, I think libc++ is like one of the best implementations probably. This technically uses libc++, it's a different library. I don't know if it's good or not. But it looks good on benchmarks, and maybe this also looks good on benchmarks. But okay, so pushback is hard to write, and pushback is hard to write, and you kind of have to know tricks to write it well, and it seems like Microsoft people don't know all the tricks to write them well. So now let's look at the function and what happens inside it. So pushback calls in place back calls has unused capacity, and the most common case is that you do have unused capacity, so then it calls in place back with unused capacity. And then this function calls my last, and my last function, if I go back to the, can I like, let's see if docking works. Aha, docking works. Let's see. So this is the function we're looking at. So my last is this function. You can see there's like 1, 2, 3, 4, 5 function calls to my last. Okay, my last calls another function called get data. Let's look at my last. Come on, really? Okay. This will be painful to find. Where's my function? All right, this is the function. So, so like we are calling this function 5 times. And you know, in the release build it would be inlined and it would be cheaper, but it's debug build, it's not inlined, we're calling it 5 times. This function calls the function get data, thankfully only once. This is the function call. Get data calls the function with a beautiful name, also get data, I think. Tooltips don't work. Oh, get second. And this is on a beautiful class called std compressed pair. So this is my pair get second. Get second finally returns us the value that we were looking for. And also you can see that at every step of the way, we call this function called check for debugger just my code. And there is some other craziness that's happening here, but this seems to be like the bulk of the problems. What is check for debugger just my code, you ask? Well, this is a new feature on Visual Studio 15.7, I think. And what the feature does is that if you were to write something like this, so I want to sort the vector, and to sort the vector I need to give it a comparison function, and my comparison function, let's say, is a times 2 is less than b plus, okay, this will be bad, let's just say it's a less than b. And so what happens before this feature was introduced, what happened was you put a breakpoint on this line, and then you pressed F11. And then you didn't get to your code, you got to a std sort implementation. And then the number of times that you had to press F11 to get to the first call to this function was apparently really large. Microsoft has this really proud post about this. Where I think they might have a video. Yeah, where they are doing std any-of, which is like a simpler algorithm than std sort, and it takes them 140 times to press F11 to get to the function that they actually want to see, like to their code. 140 times. And now you would think, okay, this is an awesome feature. It is a nice feature, I suppose, but one problem is the reason why it takes 140 calls, like presses of F11, is the same reason why our code is so slow in debug. Turns out every time you press step in, it goes into a function, into like a different function, because the function is not inlined. Turns out in debug mode, every time you call a function, you have a penalty. So this is the same reason. And you have to ask, why does it take 140 function calls for std any-of? And there's also like vector begin, vector end here, to get to the code. In fact, when I read this post, I was like, I wonder how short of a vector implementation can you write that seems like it could still be extendable to a fully standard compliant one, but would take like the minimum number of function calls to get there. And so I wrote this function, and I wrote any-of, which is, you know, how many times do you have to press F11 like to get to the function call here, right? And so it took eight F11 presses. And the reason it takes 8 is because you press F11 and it has to go to the begin implementation. Where's this code? I'm not sure. Oh, okay, this is bigger. So you press F11, it has to go into the begin implementation, and you press F11, it has to get out of this. Then you press F11, it goes to end, press F11 again, and it goes out. Then you press F11, it goes to any-of, and then, you know, like 2 more presses or 3 more presses, and then you're in. So it's like 3 extra function calls, but it's more F11 presses because reasons. So like if Microsoft STD implementation was written like this, the need for this feature would have been whatever 140 over 8 is, 17.5 times smaller than it is today. And so I argue their implementation is just bad. It could have been way better. And you know, this is why some people don't like STL. So if you use STL in your code, this is what you're subscribing towards. Subscribing towards slow behavior in debug, subscribing towards making it hard to like step through the code in debugger, unreadable code, or rather readable code, but occasionally, but completely unreadable variable names. Like, come on. Why is like the code style this way, right? What is unfancy? Like what? Why does IntelliSense not work on my last, right? Like I cannot go into this function, I have to find it myself. It's because the code is too complicated. And then why does my last go through like 3 other function calls? Now there are good reasons for some of these. Like there's a reason why the code style is crazy. It's because they're really worried that there will be a macro that's defined outside of the headers that will override some code inside the headers. So they figure, hey, C standard prohibits you from using variables that start with an underscore and a large, like a capital letter. So every single variable name that's internal will be like that. Which, okay, whatever. Why is my last called like 6-7 times here? Is just negligence, right? It could have been called once. There is no reason to call it multiple times as far as I know. It's just Whoever wrote this wasn't concerned about debug performance. Whoever wrote this was not concerned with how many F11 presses it takes to go through your code. And it might seem like I am a little unfair on the authors of the standard library, and as I said, I think they mean well. I think they're smart. I think they don't have the right set of kind of, how do I put this nicely? I think they don't have the right set of things that drive them. I think they are not trying to build the best library in the world from that checks like all the boxes, and it's hard to build a good STL implementation for a lot of reasons. But this is the most used library in C++. So the amount of effort that has to be spent, and as far as I know, the number of STL authors in Microsoft was like 2 or 3. And it's probably still this way, and maybe it's 2, right? And maybe it used to be 1 and now it's 2. And okay, yeah, like there's also this, like why are there 2 people working on a library that is used by every single person in the world who's writing C++? Okay, not every single person, but like by a lot of people in the world who write C++ code, right? Like why does that happen is also a question, right? Maybe if there were more people, then they would be able to spend more effort on making these parts of the code better. And so this is not the only problem here. The other problem here is this. So like one problem is the code is just not good, in my opinion, right? It is not terrible, but if you consider the fact that, once again, my standards for STL would have been like high. They would have been way higher than any library that I personally write. And the code in libraries that I personally write seems to be better. So that's a bit of a disconnect, right? But then there's more problems, of course, right? So the other problem is, so the other problem is the language sometimes just doesn't have enough features to sort of be able to support the things that the STL authors want. So you have conflicting requirements. So STL has to be fast in release, it has to compile quickly, hopefully, maybe. Is this even a factor? I think it is. I think they are working on compile times as well, but you know, once again, maybe not to the extent that I would have worked on them. It has to not have bugs. This, I guess, is the first requirement, but really all of these are requirements. Like if STL is slow, it's a broken product. If STL has bugs, it's a broken product. It has to be slow in debug, I argue. Oh, it has to be fast in debug, I argue. Because hey, if the library that everybody's using is slow in debug, you're wasting programmers' time. Every time they use STL, you're wasting their time. And if your game uses STL, then guess what? These slowdowns will happen to your entire game, not to just like one little function. And so then the other issue is, right, so I was saying there's conflicting requirements. So there's a requirement that the code has to be fast in release. There is a requirement that the code has to take little space in release, or really anywhere, right? Like if the size of a vector class is large, it's a problem. But then vector class has all of this, not all of these. Vectors like the best container. If this was a stream about std map or std unordered map, this stream would have taken me like 5 hours of just complaining about every single thing, because every single thing, well, not every single thing, but like a lot of things there are really broken. std unordered map is not a good container. There's way better ways to build a container like this. They require changes to the C++ standard, which is why std unordered map is bad. But this is not, this is like a failure of the C++ as a standard body, as an ecosystem of, like it should have been the case that people who would be looking at the standard would say, hey, we looked closely into hash table performance, and the thing that you're doing, and we try to implement your standard, and this is just slow. It's way slower than an alternative implementation. But we cannot do an alternative implementation because your standard is broken. Let's fix the standard. No. And I'm talking about this as if these things are really easy to resolve and the world is complicated. And I'm not saying, you know, I'm not saying all of these things are trivial to solve, but I'm saying that for C++, for C++ containers, for C++ as a language, to be treated more seriously in the community that deeply cares about performance, such as game development community, things have to change. And I don't think things are changing right now. Or they sometimes are, in small ways. So let's talk about one specific thing about state vector For this, let us look at this. So when you declare a vector, you have to pass it the type of the element that it contains, and also type of the allocator. So the type of the allocator, and you may notice that my code doesn't do that, and like this just says std allocator int, right? This just sets the vector float. So it defaults to a value that just uses global memory management operations, but you can pass it something else. And when you pass it something else, it's a class that can control memory management operations that are done by this vector object, and this class can have state. So this is an example of a new feature in C++ 17 where there's like a new way to think about allocators that is occasionally more useful, often more useful, I don't know. And this guy specifically does have state. So it's kind of important. It's important for allocator to be able to have state. So imagine you're writing a class, like a template class, that's a vector. Okay, whatever. So what does a vector need? So it needs data storage. It needs a size. The size is the number of elements that the vector has, and it needs capacity. This is the number of elements that the vector has, or this array has, which is basically how many elements can you fit there. And vectors generally grow exponentially, so you push an element into the vector, or you push like 10 elements into the vector, and the size is 10, and capacity is like 15 or something. And this is so that it doesn't have to grow this array on every single insertion. So this is good. And usually vectors aren't done this way. Usually vectors are represented like this, and like this. And this is basically data plus size, and this is basically data plus capacity. And there's a good reason why people do this. It's kind of important for reasons I will not go into. You can argue that if you never did this, you could do this, which would be 4 bytes smaller on 64-bit architectures. Like on 64-bit architectures, this or the other pointer thing is 3 pointers, so 24 bytes. This is 16 bytes. This has a limit of 4 billion elements in a single container. Unfortunately, the standard library has to support a case where there's more than 4. But really, more than 4 billion elements in a single container is kind of obnoxious, because at this point you should really have a different data structure. But I digress. In game development, a lot of people would have containers like this to save space, right? And it might seem, hey, 8 bytes is a really small number, but the reality is that in a program written in C++ that is really large, the number of objects like this is astronomical. So you could be saving megabytes by saving like 4 bytes, 8 bytes out of the thing. Anyway, let's keep it like this. So what about allocator, you ask? Well, allocator can have state. So for example, I can say, here's my awesome allocator. And it has like some integer, and it has some pointer, and it has God knows what else. And you have to store this data. So this is a natural approach, right? Easy. Here's the problem. The common case is that the allocator is not awesome, and the allocator does not have state. Let's call it empty allocator. This is what std allocator class does. There's no members inside it. And you might think, okay, what is the size of this class? So let's go to the size, or let's just go to the whatever. Let's go to this pointer version. All right. And this is one extra like tribal knowledge about sort of std vectors and how to write generic C++ code. So how big is vector? Well, you may think this is 8 bytes on a 64-bit platform. This is 8 bytes, this is 8 bytes, this is 0 bytes, because there is nothing inside it. So it's 24 bytes, right? No. The size of this guy is 32 bytes. which is 4 times 8, where 8 is the pointer size, so it's really 4 pointers. Why? So this guy takes 8 bytes. Why? So actually this guy takes 1 byte. The reason why it takes 1 byte is that C++ standard, as far as I remember, and I'm not like a standard lawyer, however you call these people, but I can read C++ standard, and I'm not gonna like go download it and find this thing, but basically it says that, say there's an allocator and there's like a second allocator for some reason, and say you have a vector of int v, and say it's a struct, so that, oh, come on, alright. So the standard says that you should be able to take a pointer to the first field, a pointer to the second field, and they have to be distinct. So they cannot equal each other. If this field was 0 bytes and this field was 0 bytes, these pointers would have to equal each other by necessity, right? Now, you can also argue that, hey, if there's just one of these at the end, it could be fine. And I don't know the reason. I think there is a reason why even in this case it cannot be 0 bytes. I don't remember what the exact reason is. It could be that the standard also says that the pointer to a field cannot be equal to like the pointer past the end of the container or something like this. I don't know. Oh yeah, okay, right. It's because, never mind. I think it's because you can like inherit, and people just don't want to deal with this stuff, so they just. So I think maybe it's because you can do this public vector like T allocator, and here you can have a field, and then if you did this, and then you did this vector 2 thing, and then you did pointer to allocator and pointer to field. If allocator was 0, then this pointers would be the same. So basically there's like reasons why this cannot take 0 bytes. So it has to take 1 byte. And then the other thing that happens is the size of the object is aligned to 8 bytes. Because it has pointers, and due to how classes are laid out, it has to be this way. Like if there's a pointer in the class, by default it's going to be aligned to 8 bytes. If you're on a 64-bit platform. So what do we do? What do they do? I'm not sure I would do this. I mean, if I were doing this, I would say my STL implementation either just doesn't have support for allocators, of course it makes it non-standard compliant, or there is support for allocators, but you know what, in my game, like the problem of saving space on this field doesn't exist, so I'll just always store this. But of course the standard container library cannot say this. It can't violate the standard. It also doesn't want to compromise apparently on memory. Apparently it does want to compromise on debug performance and release performance occasionally, but not on memory. But okay. So what do we do? So there's this amazing trick called empty base optimization, and I forgot if standard mandates that it's like supported. I think it doesn't, or maybe it now does, I don't know. But essentially every single compiler supports it. Here's what it boils down to. If you were to have a struct that's empty, and if you were to have another struct, let's call it foo, that inherited from empty struct, and if you were to have another struct like bar that contained a field empty struct, then and both had an integer after this, right? Then the size of this guy would be 8, because there is 4 bytes for this guy, 1 byte for this guy, and also 3 bytes like here in the middle because of alignment rules. And the size of this guy will be 4 bytes. It's amazing. Essentially, the rule says, the rule is complicated if you have multiple inheritance, but for single inheritance the rule says if you have one parent, I mean if you have single inheritance you only have one parent, and if this parent is empty, the parent does not take space. How can we use this? Well, let's inherit from allocator, and then, you know, like privately inherit from allocator or something like this, and this object will take 24 bytes of memory if allocator is empty, and whatever, you know, whatever number of bytes if allocator is not empty. Amazing. Now, I haven't thought deeply about whether this exact line will work? I suspect it might. I suspect there might be issues with this. And then essentially, internally, what you would do is you would say allocator, like allocate blah. And like maybe it works and maybe it doesn't, and I'm not sure. And I'd have to look into at the standards and stuff to figure out if it should or shouldn't. But this is not what Microsoft STL does. Microsoft STL says, hey, here's a really interesting generic concept. Oh dear God, they also use Finaya. All right. Oh God. Okay, whatever. So this is tricky, but I will not go over this part. This part is like insane. Well, actually, right. Okay, or whatever. So they say, hey, this is this amazing construct that you can invent, which is called compressed pair. Imagine a pair of values, a pair of types. Imagine a pair of types that you can create a type out of that can hold a pair of values. But if the first type is empty, then the size of this pair is the same as the size of the second value. And then we say, hey, maybe the vector should inherit from this compressed pair of allocator and like other stuff, where this other stuff would be a struct that contains these guys. And to get the allocator, it's a pair, so you say, hey, give me the first element. And to get the other guy, you get the second element. And this is exactly what happens here. You can see that this getData thing says, hey, I will call getSecond because it needs the struct with these three values of this compressed pair thing. And so the reason why this is a problem is, okay, first of all, it just makes the code complex, right? Like, clearly. Second, it makes debug performance slower, because in debug, nothing is in line, so everything is slower. Now, fortunately, in C++ 20, there is this feature called something, no unique address? No unique address. So fortunately, in C++ 20, they have recognized that having to do gymnastics like this is counterproductive to every single person involved. And this is just one type. Imagine what happens when you have like three things like this. Turns out the base class optimization doesn't work for multiple bases in many compilers. So you have to do like a nested structure of pairs, and it's just insane. So they have this new attribute that says no unique address that allows, doesn't guarantee anything, but allows a compiler to optimize this field away, because you don't have to guarantee that the address of this thing is unique anymore, so you can have it take 0 bytes. So you see the compiler may optimize it or may not optimize it, just like as if it were an empty base. So let's see if this is mandated by standard, by the way. So yeah, this is talking about the stuff that I was talking about. Yeah, so they can be completely optimized. And it's prohibited. Oh, empty base optimization is required for standard layout types since C++ 11. So I guess in C++ 11 this empty base thing is in some cases guaranteed to happen. But yeah, so in C++ 20, you know, no unique address will be a thing, and then they will be able to clean this thing up, and that they will say that will save us one function call. So that's great. Our code will be slightly faster. All right. Let's look at this thing very briefly, and then we'll actually solve this. Oh, then I'll look at the questions if there are any, and then we'll actually solve this problem. I'm not using the new version of Chrome. Should I? Why do you think? What's the new version of Chrome? All right. Let me finish the thought. Right, so let's look at this thing. This thing is new. This thing was like surprising, and because I never saw that before, right? So this is the implementation for this beautiful feature that I was talking about, where instead of making their code better, where it did not have to take 140 steps to go through that, they added a feature that, you know, does it in just one step in, and it's a good feature. I'm sure it's useful. It's just, it's sort of weird how this sense, like a set of priorities is, like if I had a debugger team, for example, okay, so like different teams work on different things, right? So it's not the case that people who work on this feature sort of take the time away from other teams, although maybe, you know, they should have worked on making STL better, but let's say they have a debugger team and the debugger team wants to solve a problem. How about solving the problem of debugging in release mode? And they have been working on this problem, but I'm sure, like, I haven't looked at this. I know the version that we use at work, which is 2015, it's like not great, but there's like a lot of stuff to do there, right? Or they have this thing that they're shipping now, which is reverse debugging, which is also amazing, probably. I haven't seen it yet, but I've seen a similar tool in like WinDBG, and it's really, really nice. It's like changes your mind a bit. You can step through code backwards, sort of. So they should be working on things like this, right? In favor of things like this, where they should have just like made the code better, right? I guess there's some other stuff. There's like this stuff, which is they call a Windows API function, but this is not, anyway, whatever. And like, so to be clear, this feature is fine, but I'm not happy with this feature slowing down my debug code. This feature is enabled by default in new projects. You can disable it. If you are upgrading an old project, it will not be enabled, but it's enabled. This is how it got enabled. I like created a new project for this thing because I'm using, like, I'm not using Visual Studio, so I just create new projects when I need them. Just my code. So yeah, there's like a way to disable this thing. It's enabled right now. You can disable it and this function will disappear. So here's what's happening. Here's part of what's happening. Let's disable, let's undo this thing. That would be nice. And then, so we have this profile where OBJ parse file, parse OBJ takes like 1200 milliseconds. And let's disable two things. We'll disable this thing, which by itself doesn't do too much as far as I remember, but there's this other thing somewhere. Yeah, this thing, I think. And this thing is useful, but let's disable it and see what happens. And maybe good things happen and maybe bad things happen. Like, I don't know, I haven't tried this yet. But somebody from Microsoft is looking at this problem. Like, I sent them the benchmark. They were kind enough to reply on Twitter when I expressed my dissatisfaction with the state of things. And they were kind enough to reply and ask for a benchmark. And I was kind enough to give them a benchmark. And they are looking at that. So they said that one of the problems is that this just my code feature, which is semi-expensive by itself, like you saw calls to this function. This function basically, right, yeah, so I didn't explain what the function is for. So every time it looks like, I don't know much about this, but it looks like every time you call a function from STL essentially, there is a call to this check my code thing that I think checks if you are under a debugger and the special mode of just my code debugging is currently enabled. And if it is, it changes some behavior somehow, and I don't know too many details. But essentially there is a call to this function that's inserted into every single function in debug, I think that's compiled as part of STL. So, oh wow. So disabling these two things brought the time down to like 400 milliseconds or so, and it was like 1200, so it's like 3x, right? Slightly more than 3x maybe. Let's see. Yeah, so this is like 384 now, and it used to be like 1217 or something like this. So that's like slightly more than 3 times faster. So the issue, one of the issues, and okay, you cannot, this takes 300 milliseconds. GCC took 41. So even after I disable these extra things, this code is still, what is it, like almost 10 times, like 9 times slower. Because either the compiler is still worse in some ways, or it's just STL is really bad. So you can see here that it's like better Oh dear God. Right, there's one more thing we can disable. But you can see there's no calls to this like just my code thing anymore. And also these calls got faster. And so the idea is, and I will just look at this tweet, and I wanted to like show the assembly, but we still need to fix this problem. So, but yeah, so Bill O'Neill works at Microsoft. He was nice enough to look into this problem. He says one of the issues is basically that if you enable both of these features, oh yeah, here's an assembly. So let's just look at this. So so this is the just my code thing, right? I think the mouse cursor should be visible on the stream. So this is where it says, let me call this function, and then the debugger can monitor the calls to this function somehow, and then do something about this. I don't know how it works exactly. But also you can see a lot of other instructions here. So this is on the right, you have a debug build that does not, I think it's the same configuration almost as I have, or maybe exactly. And then on the left you see the configuration that's the default, right? Like everything enabled. So the other problem is this. This RTC1 thing that I have had to disable. Where was that? Okay, whatever. Oh yeah, basic runtime checks. It just says default. So it serves a few useful functions, but one of the big things it does is it takes a stack frame and then it clears the stack frame to like an undefined value, or rather, as you can see, I think it's like CCC or whatever. And then this makes sure that your variables are not initialized, that your local variables in the function, they're not just not initialized, they are initialized to a bogus value, which is helpful because, you know, it helps you catch issues earlier. And then there's some other stuff that this code does. And then I think what happens, from what I understand, is that even if I have never tried this, but let me try to, oh no, yeah, I did try this. But I think what Bill is saying is that like these two features interact, and the just my code feature inserts a function call. And this other feature sees the function call and says, oh, this function must be complicated. Let me clean the stack. Even though there's nothing pushed on the stack, there's no stack variables. It still says, hey, let me clean the stack, or something along these lines. And this makes the code slower. So I haven't checked this thoroughly. Let's say this is what happens. So yeah, there's this other problem. This is beautiful. So this is this other issue that is a feature that I think is not implemented in C++, in libstd C++, so the comparison is technically unfair. So Microsoft Visual Studio STL implementation by default enables in debug iterator debugging. And this injects a lot of code into STL to validate the usage of the iterators, which makes it slower. And this is technically not, it's like a nice feature sort of, even though, so it's like the same thing where, okay, so you look at Microsoft and you say, hey, they are doing great, they have implemented this beautiful feature that checks iterator validity and asserts on some wrong usages of STL. And then it's nice, and then it catches some set of issues. And then you look at GCC and then, hey, okay, GCC doesn't have it. But the reality is GCC has a few features that are so powerful, and specifically I'm talking about address sanitizer and undefined behavior sanitizer, that are so powerful that they completely subsume this feature. They result in slower code, which might be slower than what we are looking at, might not be, depends. But they catch a giant class of problems. They do not require mostly to change the STL code in this really deep ways. And this is just such a different sort of way to do things and to like engineer things that, I don't know. I am looking forward to the days where instead of the Microsoft compiler, we will be using Clang. And instead of the Microsoft STL implementation, we'll be using libc++ on all platforms. And then people who really like Visual Studio can still use Visual Studio and use that debugger. The debugger in Visual Studio is pretty good. It's better than all other debuggers together. But not use Microsoft compiler stack, because it's not bad, but it's different, and it's different in really depressing ways sometimes. What was I doing? Oh, so let's disable iterator debugging and see if maybe things improve more. Hell is this macro called? In Roblox we disable this debug level thing, like in basically all builds. It's not quite all builds, but in most builds. The other thing that this beautiful thing does is it makes debug and release builds incompatible. So if you ever get a link error that says, hey, iterator debug level is wrong, this is how this feature hurts you in one more way, right? I hope Microsoft people will not watch this stream, because I'm not super nice to Microsoft people in the stream. But I feel like everything I'm saying is fair, okay? I feel like I'm not being super unreasonable, and I recognize the challenges when writing all of this code. And engineering is a hard problem, and it's not like code that I write is perfect and amazing. But I kind of expected code that Microsoft people write in STL to be perfect and amazing, and it is not. Even if you take into account the fact that C++ standard is really hostile and it wants you to do things that might be unreasonable and stuff like that. Even with that in mind, this is still not great. Alright, let's see. Alright, so 181. What were we just now? I forgot. But I remember 300 something. But the total that we started from was like 1217 and 181. So okay, so like these extra debugging features cost us 7x in runtime performance. So if you're running your game in, well, our initial delta was what? I should have written this down. I don't remember. 20x, I think, I want to say. But like, so this is saying, hey, 6.7x can be recovered by disabling features that help debugging in some ways, but not all of them do. And this feature is kind of useless. Oh, it's not super useless, but honestly, so you know, like Roblox code is being written without this feature basically for years and years and years and years, and we do use STL. And then occasionally we run without this, with this feature on, because we occasionally run in debug mode. Does not happen super often, like in true debug mode, where this thing is on essentially and some other stuff is. And I remember in the last 5 years, or 6 years, I think 2 occasions where this feature has flagged code that is wrong. And it doesn't mean this feature is useless, right? It did flag code that is wrong. But, and I'm sure there's some number of issues that we would have been able to caught with this feature, right, if, you know. So the total number is definitely more than 2, right, and like this is just me, there's like a lot of people writing code with Roblox, but, and if this feature didn't have a cost to it, then okay, it's a great feature. But this feature has a large cost from what it looks like. 7x. Yeah, so even after all this, by the way, we are at 180 milliseconds, and this is still like 4x slower, more than 4x slower than GCC. And at this point, I'm pretty sure I have disabled all of the compiler and really special sauce STL stuff, and we are just down to this function calls this function, calls this function, calls that function, calls that function, and it's just, you should not be doing that. Alright, so, let's fix this problem. Or rather, before that, let me look at chat, spend a couple of minutes to answer questions maybe, and then I feel like we'll be able to fix this problem in, you know, half an hour or less, hopefully, and then we'll see. So let's look at chat. Alright. Everyone I know calls them chars. Chars as in charred beef. Thank you. Yes, this is part of why I switched to char. Is this another stream? Yes, it is. I'm not using new version of Chrome. Yes, which new version of Chrome? What does this mean? The same shirt. Yes, this is the same shirt. Turns out if you take a shirt and then you wash the shirt, you can wear it again. It's amazing. It at least turns off just my code. Yes. So just my code is disabled when you're doing a release build. It does not affect performance in release. That is nice. Would be interesting to also define. Oh yes, I guess this was done while I was. This was a comment that was left while I was doing this. Yes, yeah. So iterator debug level is a problem. Specifically, what pointed to. Do I still have this thing? All right. But basically, yeah, there were calls to this orphan range thing in pushback somewhere. I mean, it doesn't matter that it's pushback. Yeah. So there is this call to orphan range, which is basically the iterator debugging feature, which says let's mark all of the iterators in this range as invalid. And what this function does is that it goes through a list of all iterators that it knows exist. And this also makes iterator construction slower because it has to maintain like a global list. And it also has to enter and leave a critical section every time it does this, because it has to keep track of this list of iterators, right? And it says let's mark them as invalid. And you know, that's like cool and stuff. But yeah, so GCC has address sanitizer and Clang has address sanitizer, and there's a very large class of problems that are disjoint between these. Yeah, I guess, sorry, I meant undefined behavior sanitizer. So I thought undefined behavior sanitizer has a feature where if you create a pointer that is not, if you have like both asan and ubsan enabled, maybe it doesn't, I forgot. So maybe it fixes, maybe it catches like a unique problem that you can't catch with any other tool. I'm not 100% sure. And this problem does happen sometimes in production. But yeah, it's just like the cost is kind of astronomical. So, yeah, without iterator debug level, it makes things better. So if this was the level of performance always, so we, well, okay. When we disabled iterator debug, so right now we are running with iterator debug level. So this is like much faster already, right? This is, we disabled just my code, and this other thing that is more useful. Just my code, honestly, almost should be like off by default, because I don't know. Maybe I'm wrong. It also feels like there's like other ways to implement just my code that don't have runtime overhead, and I'm sure Microsoft people talked about this, and they know way better how their compiler stack works, so I will not judge their choice for like this just my code thing, even though I don't like the feature. I wasn't like pumped about the feature when I saw the feature, but now that I saw it hurting performance, I'm like, okay, I don't like this. But whatever, I will survive. And it's probably fine. So yeah, so if debug performance was always like the same as it was when I just disabled the 3 features, I would be probably less upset about this whole thing. But I don't want to, you know, be constantly having to disable features that are enabled by default in Visual Studio. So the sensible solution is to stop using STL, which is exactly what we will do. Oh, you've been throwing away all your shirts all this time. Man, you are missing out. You are missing out. Although, yeah, anyway. This is not a fashion stream. I'm not a person to hold a fashion stream. So, let us change this code, remove STL, and see if it gets better or worse, or what happens to this code. And I'd like to take like a performance benchmark, just, you know, just for fun. So remember, this is not super scientific. We are measuring noise to an extent. Like, I don't know. Like, don't treat, like, we will write some new code that doesn't use STL. We'll look at the performance. Don't read too much into whatever performance numbers we get, except for these performance numbers being much better on Microsoft Visual Studio. So I want to just very quickly, bear with me for a sec. I want to switch this project back to be building my test bench. Add this one, remove this one. And then debug -d. So this is what it is. So this is debug mode. Oh, I was writing some code with, okay. So this is debug. This is the same thing that I was, all right. Let me disable tracing as well. This does not affect performance of OBJ parsing. This just prints out stuff in simplifier, which we are not even talking about today. So that's nice. So that's the debug build, right? So we have like some quantitative data. That says, hey, indexing is like, okay, oh, here's the difference, right? So this thing is not, this is my library code. It does not use STL. This is my demo code. It does use STL. The delta is kind of shocking, right? So this is like less time than we had when we were running under a profiler. This is because profiler has a bit of an overhead. So, remember, plus or minus 10%, but this is like not 10%, right? This is like a large delta. So this was debug. Now let me time release, and I want to also time debug without all of the beautiful and amazing features that Microsoft has. This, oh my. Alright, let's do this again. I forgot to switch. Alright. So, right. So, yeah, I sometimes work from Visual Studio, sometimes I don't. When I do, sometimes I work on one program, sometimes I work on another program, and I have to like switch things around occasionally. It's nicer than maintaining 2 project files, although it might not seem like this since I have to do this thing now, but I don't have to do this thing often. So there's that. Alright. Oh, and okay, debug command ups. All right, so debug performance, release performance, I should say, is actually good, right? You can see, like, OBJ file parsing might be slower, might be faster, who knows. This thing might be slower, might be faster, also who knows. These seem like large deltas, but they're like 3 milliseconds and like 10 milliseconds, and this could be just noise. And you need a more, so I ran it again, it's like 25 now, and this is 886, right? So this is just noise. So you need a more sort of, you need to be scientific when you compare performance across, these like small deltas and ranges. Like, is 31 faster than 25? It's hard to answer this question, right? It is easy to answer the question of, is 1000 milliseconds faster than 41 milliseconds, unless this is an outlier, which it isn't, because we can repeat it by running it multiple times, right? Alright, and so let's just pick, it doesn't matter. Like, let's just take this one because it's closer to GCC, but the reality is basically these numbers are noisy. That's fine. Alright, a really quick debug build, disable everything. Debug build, right? Microsoft. Alright, where is this again? So disable. Oh yeah, right. So this is the thing that it's doing, right? So it's basically doing 2 things. One is it cleans up the stack so that uninitialized variables are actually initialized to a specific bogus value. And the other thing it's doing is it inserts extra checks for access to stack variables, so that if you write past your stack array, it can be flagged in debug. Address sanitizer can do some of this stuff. So there is that. I wish Microsoft address sanitizer is like the best thing that happened to C++ in the last 20 years, unquestionably. C++ 11 does not compare, not by a long shot. None of the C++ versions do. Address sanitizer is amazing. If Microsoft had address sanitizer, which they don't and won't because it's a different compiler stack, then, if Microsoft implements address sanitizer, I will retract every single bad thing I said today about their STL implementation. I will say it's amazing. Wait, was GMC like off just now? Alright. Let's just measure this again. Yeah. If I were Microsoft, I would be like just looking at really tight integration between Clang and Visual Studio out of the box. I want to click a button and it should work. because, man, they will be gaining so much stuff with that. It's amazing. So, stripped or something, I don't know. Like, we removed a bunch of stuff that was wrong. So this is like substantial, right? So it's still like 5 times slower, give or take, than GCC, but this is not terrible anymore. Now let's reset it to defaults, and let's reset this guy to defaults, and then this is the actual state of debug. What? I'm not like, and so remember these settings, it's not like I enabled them. No, they are on by default in debug builds. Yeah, so this is just catastrophic. So yeah, like a second and okay. Alright, so these are our timings, this is great. And then let's just replace STL with something else. And we'll see how that works. How often does Roblox write alternative behavior just because STL is slow? How much STL is used? So we use a few STL containers. We basically use vector and string mostly. Don't use unordered maps. We use like a few others rarely, but we have our own hash map that we use in performance critical parts of code. It's way faster than standard hash map, like way faster. Like up to an order of magnitude faster on workloads that we care about, on some workloads that we care about. We have our own array, dynamic array class that we use in some places of the code, but we haven't like extended it enough so that it can just work as a drop-in replacement and just started using this like everywhere. We should do this. So the other like thing, for example, that std vector doesn't know how to do is, say you wanted a vector with 1,000 values, and then you wanted to fill them one by one later. You can write code like this, where you make a vector you reserve and then you push back. But then every time you call pushback, there's an if statement here, and some other code that tries to resize the vector. So this is slower than it could have been. The other thing you can do is you can say, instead of reserve, you can say resize, and then just fill things like this, right? And this is nicer because there's no if statements here, so this directly writes to memory of the vector. But what you pay for this is that this resize guy initializes the vector with default values of this struct. And if this is a struct, you can work around this in some cases, but like in this case, this guy clears the memory with zeros. And okay, clearing the memory with zeros is fast, but it's slower than not doing it. And in some cases in our code, we have to work around this. This is why we have our own vector that we don't use all the time, etc. Yeah, so, but Roblox codebase has organically evolved from using a lot of STL to occasionally using some other stuff to maybe one day we will stop using STL. It's hard when you have a code base that is continuously developed, that ships every week on many platforms, that has been developed for the last like 15 years, not 15 but like 12 years, right? And it also happens to have like 70 people or something, more than 70 people probably, like 100 people by now, I don't know, like a lot of people working on this code base at the same time every day. It is really hard to make sweeping changes like this. I hear Google is really good about doing stuff like this, where they have a lot of good automated tools about taking a giant, enormous C++ code base and just like automatically replacing usages of one container with usages of another container correctly across multiple subsystems, etc., etc. We don't have tooling like this yet. Maybe we'll never will. Maybe we will. We'll see. All right. So. Mission statement, remove STL. It's been like an hour and 40 minutes. So we will have to run a bit over 2 hours because I don't know if I can do this in like 15 minutes, but whatever. So let's just replace this. Fundamentally, here's what we need. We need to replace, instead of vectors, we could use some wrapper struct or class or something. But I kind of want to see, do I want to see, let me think about this for a second. Yeah, maybe I should just, alright, yeah, you know what, let's just take the brute force approach. Here's the brute force approach. Let's create an OBJ vector. I didn't have to implement, do I need like a copy constructor for this stuff? Maybe it's more painful than I thought it would be. Let me try to recall. Oh no, yeah, this is not okay. This is fine. Okay, so let's just make a simple struct, and it'll have like a default constructor, or rather, oops. Oh yeah, that's fine. And we are too lazy to. It's not like it's hard, but more like we are too lazy to implement copy constructor and assignment operator, and this really should return. So let's just say that we don't support assignment, we don't support copying, we support nothing. In C++ 11 you would say this. Remember, this is not C++ 11, this is C++ 98, or at least it should support C++ 98. So yeah, we will just roll like that. So the vector will have a data pointer, size, it will have capacity. Note, I'm not putting this behind accessors. This is because I want the debug code to be fast. And you can ask, hey, what happens if I wanna change the size, if I accidentally change one of these guys externally? And I don't care about this. I want my code to be fast. So my code will be fast. And I will disregard stuff that I don't care about. Okay. And of course we need the destructor, where we will delete. So the real vector implementation is complicated. The reason why the real vector implementation is complicated is because it has to support complex types that have constructors, destructors. There's really special handling for this. Like if you have 5, if capacity is 5 but size is 3, the last 2 elements are not initialized, and there has to be special code that handles this. Guess what? We don't care. So we will call this POD vector, which stands for plain old data type vector. This is to highlight the fact that we don't care. And in C++ 11 you can probably do something like static assert, like std is POD t value, the type has to be pod, but this is not C++ 11, so we will not do this. This class is single purpose. The only reason why we wrote this code is because we need like 5 of these guys, and I don't want to think about sizes and capacities of stuff like this, of these individual things. In fact, we could go even further. Let's go even further, okay? And say this. This is just... should I? Alright, no, whatever. Let's just keep it like this. This is fine. Yeah, I was thinking maybe like OBJ file should do this, but whatever. That's fine. Okay, this is good. Alright, so we have a vector. When you initialize the vector, it's empty. You can, when you destroy it, it just kills everything. How do you add data to this vector? Well, for this we need a function. And a straightforward approach is to add a function called pushback that takes an int, or sorry, it takes like a t, right, and write some code that does this. Here's why I don't want to do this. So the typical use in this code is we are pushing multiple elements at a time, and so we cannot know how large the vector should be. Or we could if we like went through the file one extra time or something like this, but the problem is basically OBJ file doesn't have a header that says this is how many vertices this file has, right? So we kind of do things incrementally, which is not great for performance, but whatever. But yeah, we push multiple elements at a time, always. And you could refactor this code to use a struct, and then you won't have to do this. But I don't wanna do this, it's like too much work. So instead, what I want to do is, instead of a pushback function, I want to add a function that just says reserve space in an OBJ POD vector team I have a function, and so the idea is you call this function, and it will make sure that you can write these many elements to this vector. And so if v size is if v so I'm cutting some corners here. There's some really edge cases where if count is large, this addition can overflow. What should we do in this case? I don't care. I guess I could just do capacity minus v size, and I could even assert v size is less than or equal to v capacity. Should really always be true. And then if this thing, so this is like how many elements remain, and if this thing is greater or equal than count, then we are good. Okay, scratch this. This code is now overflow safe, or rather underflow safe, or safe. So if we ran out, we need to reallocate the vector. So we need to allocate space for what am I doing? Alright, so we need new capacity. So how should we compute new capacity? So let's say we had a vector, it had 5 elements, it had space for 5 elements, we need to push, and it had like 4 elements, we need to push 2 more. So we need to increase the capacity up until it's big enough. How are we going to do this? Well, we want to grow the vector exponentially. The way we will do this is this. This is relatively standard. I usually use like, the vectors usually grow like 50% at a time. So we will say that we will start, if the old vector was empty, then we'll start with some moderate number of elements, like 16 or something. Which really is too small for this kind of code, because it has to deal with large meshes, but whatever. And otherwise, we will just start with... I could like cut corners here, right, like crazy, honestly, because the input value here is small. Should I? Alright, I won't cut corners. I will be slightly less. I could write code that's shorter, but I will do this. Okay, so let's start with either the current capacity or 16 as the minimum one. This makes sure that the first realloc, it goes to 16 at least, right? And then while new capacity is less than the capacity that we need, and the capacity that we need is v size plus count, we will multiply this by 1.5, but this is a floating point multiplication, so instead of doing this, we will do this. And this is, yeah, so this is faster. So now we'll do this. So we have the new capacity, and we could assert that it's like larger than size plus count, but we just did this, so what's the point? So allocate new data. So then we need to copy a bunch of elements from the old container to the new container. And in std vector, you would do like std copy, or it's like std uninitialized copy or something. But we are dealing with pod types, so we'll be bold and just hey, copy this. And we only need to do this if v size is greater than 0. The reason why I care is because memcopy is not defined for null pointers, and this thing starts as null pointer and whatever. C++ trivia, not interesting. So we need to copy v size times size of t. And then we need to delete v data equals new data, v capacity equals new capacity. Alright. So there's no error checking here. This is because if this guy fails, we throw, or rather C++ runtime throws an exception, and this matches behavior of std vector. And you know, in a more ideal world, this would return a boolean and we'll check it at call sites, but I don't care. You might have noticed that I'm committing the same sin that I was just talking about, where I have this function that's kind of large, and there's a fast path here, and compiler may inline it or may not inline it, who knows. So we will say that there is a reserved space slow, which should only be called if, so this is just vector consistency check, and it should only be called when we actually care about resizing. Or does it matter?
I mean, like, whatever, doesn't really matter. It's fine, it will work either way. And then here we will basically say, oh, do we need this guy? I mean, fine, let's leave it, it doesn't matter. And otherwise, we'll just reserve space slow v count. And so this tries to make sure that this guy can be lined, and even if this guy... What just happened? Oh, like it jumped to a different file. Okay. So this makes sure that this function can be inlined even if this function cannot be. Alright, who knows if this function works? It might work, it might not work. We will figure it out. But yeah, the idea is if we have enough space, we have enough space. If we don't have enough space, then we make a new vector. And then after this, hopefully, you know, v capacity minus v size is greater or equal than count. And we should probably keep this assertion here. It's a good assertion. There is a bit of redundancy here. This assertion happens twice on the slow path. I don't really care. Yeah, we could say that instead of this count, maybe we should do this. But then it's not reserved space, it's like, alright, whatever, let's just not worry about this code much. It might work, it might not work. If it doesn't work, we'll find out. We'll step through this code. Okay, so then let's go to every pushback. Here's what we are doing here. We are pushing 3 floats, alright. Let's reserve some space in the result v for 3 floats. And then, how do we add elements to a vector that already has space? Well, you know, alright. And okay, it's like slightly less readable than pushback, but the beauty of this code is there is no function calls here. Like no, like 0, right? This is fast in debug, and it's fast in release, and there's no way to mess up this code in terms of optimization. Now, there is a way to mess up with this code when you're writing this, like if I accidentally do this, then my code breaks, but this is where kind of priorities come and play, right? Like, what do you care more about? Do you care about the code being super fast? Or do you care about the code being super readable? Do you care about debug performance? Do you care about release performance? C++ people have this concept of zero cost abstraction that I wanted to talk about on stream, and I didn't. And maybe I'll just talk while I write code, and hope I don't mess up the code while I write code. Yeah, so zero cost abstraction, there is this notion of, hey, so like, what if we could have our cake and eat it too? What if we could have code that is beautiful and expressive in code, like when you write it, and then it's really fast when you build it? And people claim C++ is the great language for doing zero cost abstraction. And people disagree on what exactly zero cost abstractions mean. Some people say that what matters is runtime performance, and this is the only thing that matters. And that's the definition of zero cost abstraction. And if you care about other things, you know, zero cost abstractions don't care about you. I don't really like this definition too much. I like the definition of zero cost abstraction where you're like not really playing with anything that you might care about. I care about performance, I care about compilation times, I care about my code's binary size. What else do I care about? I don't know. These are the big things. I mean, I care about my code working as well, right? And I refuse kind of to use the term zero cost abstraction in this way where you pretend like the only thing that matters is performance in an optimized build, and compile times are important. Because who cares how long your code compiles for, right? No, I refuse to work like this, and I really am afraid that I have committed a few horrible errors as I was, you know, rambling about zero cost abstractions. Hopefully that didn't happen. So if v is char fv, oops. Yeah, so like in this case, basically we didn't care about, we could have used the pushback function call and it would have been the same speed because it's just one element that we're inserting. But in the words of Mike Acton, when was the last time you have inserted just one element into the vector? Turns out once. And then there was like 4 call sites with 3 elements. So that's nice. Alright. So we fixed that code. We need to fix some other code. So this is validation. You notice that like, so std vector has this size member and I have a size member, but their member is a function call and my member isn't. And this is nice because, you know, debug performance is important. So let's make debug performance better. So that's cool. And then there's this function which does some other stuff. Oh, and this function is weird because it's like, yeah, and I need to do .data here. And I'm being sort of slightly inconsistent. So the other thing that happens in debug is, with std vector, is that this thing is a function call because there's an operator overload. And I'm not doing this here. I'm being slightly inconsistent because I actually have like an array wrapper for my actual library. Meshop buffer. But there I do have this thing that does a check and debug. And I thought about maybe removing this, and now I'm thinking that maybe here I should have had that. So I'm not being super consistent here. But let's just, oh no, by the way, what was I talking about? Zero cost abstractions. Right, yeah, so basically, like, if you have this amazing library that compiles into 3 instructions for these like 3 lines of C++ code, but then to compile this thing, you have to spend like a second per CPP file. I refuse to call your abstraction zero cost, because you know what, it has a very real cost to me. It is my productivity as an engineer, it is my frustration as an engineer, which is basically my quality of life, right? So yeah, there's that. So if this code was written in C, these problems would not exist in that manner, at least, right? This is the code that you would have written in C, sort of. Like, this is the code that you would have written in C, and this, you would either just spell it out here, or you could write like a semi-type-safe wrapper around this thing and call it with a macro or something like this. But like, this is why there's this interesting difference between C++ and C programs, where C programs in debug are pretty fast, because they don't have these layers of craft and abstraction that serve a purpose, but for everything like this you have to ask, what am I giving up by using this thing? And what am I gaining by using this thing? So what C engineers do is they say, I'm not gaining much from a thing like that. I don't even have a language facility to do a nice thing like that, but I don't want it because I don't think I'll gain much. Simplicity of the language and predictability of performance and all of these things are more important to me than the perceived ease of use. And you know, they may be right and they may be wrong. I empathize with C engineers for sure. Alright, so what are we doing here? Oh, there's another std vector here. What the hell is this thing doing? Oh, that's like a temporary thing because we can't triangulate in place. Oh, okay. Alright, that's fine. That's totally fine. And you will notice here, like, I was actually paying the cost for a mem copy there. So, alright, so let's like reserve space for this thing here. We don't even need to change the size of f technically here, so I'll just leave that as this. And yeah, you know, this .data gets a bit repetitive. So, oh, in the C program, right. So in the C program, like, you wouldn't write this stuff. You would just say that this is like a float pointer, and this is a float pointer, and this is a float pointer, and then separately you would just store the sizes and capacities of these arrays, and then you just remember to like match them together. And if you mess it up, you get a bug in your program. But if you don't mess it up, your program is fast. So that's the trade-off. So yeah, Do I like just want to use std swap, or should I just not use std functions at all while I'm at it? Do I use anything from std here? No. Okay. Oh yeah, right. So I will not go into what this thing is doing. Let me just do. Okay, so I will do memset result of v3 total indices. It's technically like result of v size, right? Yeah. Okay. Because this thing is. No, wait. This is the wrong thing. No. This is right. This is good. Right. Why was it total indices over 3? Oh, yeah, right, okay, never mind. Oh, okay. So this is slightly painful to write with my beautiful vector. And it's kind of redundant, but I don't want to go into the details of what's going on here because it's kind of late. And we haven't even run this code. All right. All right. You know what? Whatever. Let's just. Tempted to just use stat swap and call it a day. Let me use stat swap, call it a day, and then I'll change this maybe. Stat swap. I really hope you won't have to like debug this code for eternity, because. And so right, so like in a code base basically that's mature, you would have something like this already, and it would be slower than what we are writing right now, because we are like extreme, right? Like everything is public, there's no accessors, no operators, nothing. But it would be way faster than stat vector, and then you would accept some amount of performance loss in debug for accessibility of the resulting code. What am I? Result f, right? And then I want result fv, let's say, and then fv, and there's some shadowing here, and this is all horrible, and I don't care right now. V reserve space fv. Size equals this thing, and then memset data 3 size. So yeah, like what was one line with stat vector is like 4-5 lines with this thing, and this could be better slightly, but I don't care. Let's just build our code and see if it even works. Alright. So C++, Microsoft Visual Studio has nice features, right? As you can see, I'm like fixing errors without even looking at them. This is because there's this tiny red squiggly that's barely visible, but it is visible, and it allows me to just look at a bunch of places in the code and fix them without looking at this, which is nice. Alright, now we have to fix calling code, and there's not too much of that. And maybe at this point, maybe we should have like implemented an operator. But I kind of want to have raw performance of this code, and then we'll see if an operator makes things worse or better or what. So there's a bit of boilerplate, and I have to do the code compiled. I have to do the exact same thing in this other thing. Let's see if it runs. It doesn't. This is what happens when you write a new implementation of a thing. It doesn't work. Oh, iterator debug level helped us. How did it help us? Oh, the vector was empty. It didn't actually help us. What's going on? Oh, file of size is 0. Why is file of size 0? Did we mess up the swap thing? Yeah, we never. Alright. Okay. Alright. Alright. So this code may work, this code may not work, who knows. It's not actually very fast. I was hoping for something better. New vector debug. It takes like as much as stat vector, about as much as stat vector. So that's not great. That's not great. I was hoping for something better. Let us. So to be clear, we are like still way better than the. Maybe I shouldn't feel too bad about this. Here's what we got. With all of the crazy Microsoft debug options, with our vector, we are as fast in debug, and I don't know if our code works, but it probably does, as fast as debug, or slightly faster in debug, than the stud vector implementation with Microsoft Visual Studio, with like half of debugging options disabled. So if we were to disable the debugging options, hopefully we would get faster. I don't know by how much. That's an interesting exercise, right? So it's like, and we haven't like profiled our code yet, but it seems unlikely that there's much that could go wrong in the amount of code that we have written. Alright, so this is Microsoft Visual Studio Debug with, oh wow, okay, alright. So new vector debug stripped, which is basically crazy debug stuff disabled. So that's pretty good. That's like on the level of GCC's thing. Let's look at release. So, and it will be hard to tell if like release got faster or not because of this noise problem that I noted, but it might be faster or it might not be faster. It's probably not. 25, 25, 26, 30, that's like non-scientific debugging, super non-scientific. So it seems like it's roughly the same speed. So I was hoping to get a tiny bit of performance by like avoiding these ifs here, but I didn't get that. So okay, that's fine. Let's do, oops, this. Oh right, yeah, so we have to fix, no? Oh, we don't need this at all. Yeah, so size T is like not a built-in type in C++. Right, so we haven't fixed the main CBP program, which is unfortunate because, you know, oh. No, wait, we totally have. Oh, right, it doesn't include, okay. I like C++. C++ is a great language. Alright, so 49, 20 something. Is this like better or worse? What is it? Is this? So this is same ballpark, slightly slower, could be noise. Alright, so basically this is okay, so these results are sort of encouraging in a weird way. This means we could end the stream on a positive note. The positive note being that libc++ implementation is good enough that the delta between the custom vector that tries to be really optimal, and maybe is really optimal, or maybe isn't, let's run the profiler, is small. Unless we are doing something stupid that I forgot about that we can fix and get faster, but I doubt that. So the real issue is, right, Microsoft Visual Studio debug implementation of STL is not very good, and Microsoft piles a lot of debug functionality into STL and their compiler, which makes it even slower. But libc++ is fine. So basically, if we use libc++ to begin with, then we probably would have been in a good shape. It's hard to know without doing like a test. And I could try to compile libc++ with Microsoft's compiler, but that could take a while. So we will not be doing that today. So this is new vector. Alright. So conclusion. Microsoft STL implementation is kinda not great for debug performance. It's kinda not great for release performance in some versions. Although, as you note, so once they fix the pushback issue, in release we are like same speed. Like, I mean 25.19, but when I ran this thing again it was 25, so it's probably just noise. So it's probably roughly the same performance in release, which is nice. It is way slower in debug. You can disable a bunch of debugging features and it's still way slower in debug. But that's a STL for you. But if we used libc++, we wouldn't have any problems. So if Microsoft ever switches to libc++ by default, or if they ever take like a really close look at their STL implementation and remove everything from it that doesn't seem like it gives value. For example, the 5 calls to that my last function in STL implementation probably doesn't have a lot of value. Probably just 1 call is enough. Then, you know, things would be better. But things are less terrible than what I thought they would be. Like I was hoping that I would maybe get a tiny bit of performance over the STL with my custom thing in like release or in GCC or something, and it doesn't look like this is happening. So that's nice. And also it doesn't look like Microsoft has cached the debug symbols properly, which is less nice. What is it doing? Alright, so this is kind of what I wanted to talk about today. There is no questions in the chat, but people are still watching the stream, so I guess they didn't get bored and left. They just don't have anything to comment on. So yeah, this is kind of what I wanted to talk about. I complained a lot about Microsoft Visual C, STL implementation and compiler. We looked at a bunch of implementations of std vector, covered a few problematic cases, looked at Microsoft's one that feels to be way weirder than some others. Hopefully things get better over time, because I think things do get better over time, right? So I filed this pushback thing for release. It got fixed. And this is nice. It got fixed kind of late, but then again I filed it really late, and I don't even think it was fixed as my feedback. I think it's just sort of things aligned in this way where when I got upset enough, like I knew the problem was in 2015, I somehow assumed the problem is fixed in 2017. This is like a bad assumption to make. And then when I checked in 2017, it was still there, and then I forgot to file the issue, and then it was still there, and I'm like, I'm done with this, I'm filing this. Part of the other thing was that I had experience with Microsoft bug reporting before. And let me tell you, in 2012 or 2011 or something, they used Microsoft Connect, and Microsoft Connect was way worse. So it was basically most of the feedback that you got was either from bots or from people who don't have like a name. So you would get a reply from a bot saying, hey, your feedback is like really important to us, we will look at this at some point. And then, you know, half a year later, there's no comments. And then, you know, somebody replies to this. You don't know who they are because it's all anonymized. But they're like, yeah, we will consider this thing for a future release of Visual Studio. And then they close the issue without having fixed it. And then you just don't know what the hell is happening. Like, is it fixed? Is it going to be fixed in the next version? Is it fixed in their current internal version, but, you know, like, it's just not live there? have they just given up on this issue? Do they not care? Like, it was super opaque. The new thing, and this is kind of why I subconsciously or maybe consciously avoided reporting bugs, but this new process seems to work super well. Like, you can report bugs, they look at bugs, they triage bugs. It helps you if you ping them on Twitter or something, but even if you don't ping them on Twitter, they react, right? And then they fix bugs, and they may not fix bugs on the schedule that you really want the bugs to be fixed. But also, hey, so like there's 8-point releases of Visual Studio 2017. I think many of them, I think like 3 or 4 happened this year, right? So they iterate quickly and they are able to fix issues quickly and they do respond to feedback and things are getting better. And you know, I filed this bug that were discussing today. And once again, there was Twitter communication, so maybe that helps. But they're looking into this and maybe they'll make things better. And there were other things that they improved in STL. And things get better over time. So I'm like cautiously optimistic. The hell? Okay. The profiler didn't do the right thing. The profiler was helpfully profiling OBS and scripted sandbox. And OBS seems to take a lot of time in libx264 codec. This is probably because it's recording a video of this freaking stream. What are you doing, Visual Studio? So you know, sometimes it doesn't work very well, but sometimes it does work very well. So yeah, so this is like debug profiling of the thing. Oh, there's still like a state vector in the outer layer. This is fine. There's nothing here. This code seems to run pretty fast. 27 milliseconds, really? So this is like really fast. I mean, there's like more here. So I guess things add up. Oh, and we still have this beautiful pushback problem, right? But we have this in like, oh god. Like my demo program still uses std vector. We only replaced it in this OBJ parser. So it still uses std vector, it's still kind of slow. I won't bother fixing that part. But yeah, so this worked out, and one day the STL maybe will get better, and then maybe if Microsoft engineers do watch the stream, and then they don't, maybe they won't mind too much my slightly pessimistic view on the technology that they're building, and then we'll make it better. And then maybe I'll do another stream that says, hey, Microsoft STL is amazing, look how far they have come in just 6 months or whatever, and look at these things that are so much better now, and it's as fast as libc++ or faster, and things are amazing. Or maybe we'll look at this again in a year and libc++ still beats Microsoft like 10x, whatever it was, 40 to default settings, 40 to 1000, 50x. And once again, not apples to apples, Microsoft is enabling more stuff, but oh, before I answer the questions for like 10 minutes and end the stream, just out of curiosity, so I was talking about this fact that address sanitizer is freaking amazing and it changed the world of C++ forever, and it really sucks that Microsoft doesn't have it. And Microsoft has this debug stuff that tries to make things more debuggable, like tries to discover problems quicker and debug, but as we've seen between their STL implementation and these features, the overhead is just insane, and these features alone add like 5x the overhead. So just out of curiosity, and I don't expect this to be super fast, but let's try to use address sanitizer. Oh, this actually runs both address sanitizer and undefined behavior sanitizer, so this will be slow. This is like 2x. Oh my god. Alright, so ignore this thing. This is like this Linux subsystem not playing nice. They fixed it in the new release of Windows, which will go out later this year, I think. Okay, so we enabled this like really aggressive debugging mode, and the program is twice as slow. Only twice as slow. Why do I say only? for example, here's the class of problems that this thing catches now. So let's see. So I have this vector, and I say, hey, I want to have these many indices, these many elements in this vector, and then I just write data to this, and these writes are completely unguarded. So let's say I underallocate this vector, and so when you run this, your code may crash. It may not crash. It may corrupt memory later. It may do whatever. When I run this under address sanitizer, it says heap buffer overflow before the heap is corrupted. This is the call stack. You can use GDB to break here. The address that you're writing is located 0 bytes to the right of this region that you have allocated. It detects the precise byte, like the first byte after the allocation that I'm writing to that I don't have a right to write to, because there's not enough memory here, okay? Microsoft's compiler will, the program will probably crash in a similar place if I run it on the Visual Studio. This is not the first problematic, right? This is one of, not the first. The program might have already corrupted data. It happened after the fact, and now if I inspect the program state, it might already be weird. And in some cases, depending on the amount of this overwrite that I'm doing, Microsoft's stack would never tell me that this is the problem. Now it would if I were using std vector, right? But std vector with all of these debug checks has an insane amount of overhead, and this thing is like twice as slow as a debug build. This is impressive. I expected worse, but it does so much more. Oh, it does so much more. Like I can do, okay, so this is like a stupid thing to do, right? Like you can do this. You have allocated an array of data and then you write into the previous byte. Watch what happens when I do this in Microsoft Visual Studio. Oh, this is scary. I don't know what it's doing. Nothing good. It should have done something by now, right? What is it doing? Does anybody know? Here's what happens. This is beautiful. Oh my god, this is beautiful. So we have written to the element just before the allocated bytes. This has corrupted the heap metadata. I think we are hanging on the code that deallocates this vector way after the fact. Like here, I think, right? Like here, oh, it's even in a different function. It's like way after the fact. Or maybe it is in the same function, let's see. Oh no, it shows a message box. Does it show a message box? There's no message box. It's hanging in the message box function. Oh my god. Well, okay, so basically this is way too late, right? It doesn't show me the problem. It tells me way after the fact that the problem has happened. In large systems, in games, you can spend weeks and months chasing these issues down. There was an issue on FIFA one time like this that I think we spent a few weeks chasing down. There was no address sanitizer at this time. No debug functionality, none of the debug STL, none of that shows the issue, but the issue is there. In Roblox, we have cases where we spend a lot of time chasing down issues like this, because not everything can be caught with, debug STL and these debug compiler checks. So watch what happens here. So, heap buffer overflow at line 371, and once again, if I ran this under GDB, it would break at the correct place and whatever. 371. What do you think is at this line? Wait. Alright, right? So this is amazing. So this tool is the best tool written ever. And there's way more. In the mode that I compiled it as, It's not just address sanitizer, it's also undefined behavior sanitizer, which does like a lot of checks that try to help you I don't know, so yeah, as I mentioned, I don't remember if the pointer thingy is like detected. It might not be. Let's just see out of curiosity. So let's say that there's an end pointer that's like f data plus f capacity, and let's say there's like an f and 1, which is f and plus 1, and I think this probably will not do anything, but let's see. Well, other than complaining. Okay, yeah. Yes, it doesn't quite catch this. Like, this is undefined behavior. It doesn't do this because that might just be too slow. It does do some things, like if you do something like this, and then you say this, it should tell you, great. So it says signed integer overflow because this is not valid for reasons that are too long to explain. And if you just ignore this, compiler can miscompile your code, and this has happened in the past to many programs, where like security checks for buffer overflow would be elided by the compiler because this is not valid to do. So compiler says, you cannot do this, I don't need to compute this value. Anyway, so the fact that it's like just 2x slower, okay, and it does so much more than these Microsoft Visual Studio debug modes, tells me that people who said we wanna add address sanitizer, this is a large project, there's a lot of really good engineering that happens there, we need to focus on this, we need to get it done, it has to work really well, it has to be fast, it has to be practical. I heard Google, I would not be surprised if other people do this, runs a portion of their production servers with like an ASAN binary, or like some stripped down version of an ASAN binary or something like this. That's like not like 2x slower, but that may be like, I don't know, 10, 20, 30% slower. But if you run like a 30% slower service on like a small percentage of your fleet, of your server fleet, the performance impact is not like catastrophic, but you can improve reliability so much more because you will catch these issues really early on that then could take your engineers like weeks to find and fix correctly. And you will catch user data corruption and God knows what else. So address sanitizer is awesome. I wish Microsoft, had address sanitizer that takes 80 milliseconds with libc++ in debug builds instead of the thing that they do right now, which takes 1,000 milliseconds in debug builds. Alright. So that is where we will stop. It's 9:27, so it's like 2.5 hour stream. I wanted to do a 2-hour stream, but this seems fine. Slightly longer. If anybody has any questions, I am willing to answer questions for like 5 minutes or so, and then we'll end the stream. Thank you for being on the stream. I hope this was educational to some of you. A lot of people who write C++ code don't know a lot of these really intricate details about how do containers work, how are they implemented, what are the trade-offs, like what does the code inside look like. Because I mean, it's understandable, the code inside is so scary, you don't want to look into that. It turns out it's important to look into this code. It's important to have really high standards for code like this that is used by millions, hundreds of millions, like billions of people. If you count like users, not programmers, then it's basically billions of people around the globe use STL. I'm pretty sure every single human who uses any sort of technology uses STL in at least one product every single day. Like, this is definitely a fact. So it has to be extremely high quality. It has to be highest quality ever product. And libc++ looks pretty good. And Microsoft Visual C STL I am not super impressed with. But they will get better, hopefully, over time. So thank you for watching the stream. I don't have a schedule for,
future streams. I don't know what the topics would be. I know I'm not streaming anymore this week. It's been like 2 streams this week, and also I did a stream on Sunday, so it's like almost 3 in depending on how you count the week. But streaming seems pretty fun to me and to other people apparently. So we probably will stream again. I will think about what would be fun to talk about and to work on or to work on stream, and then we'll see. So any questions, let me know. Let me double check I didn't miss anything. Yeah, hopefully like the sound was alright. Somebody says less mic picking, which to me implies that there's still some issues with the mic, but it's reasonably good. Let me double check what it is now. There was a bit of background noise, which is not great, but otherwise it was fine. Yes, it's a bit too loud. There's like a bit of picking, but it's no way nearly as terrible as it was last time. It should be super watchable. This will be on YouTube, obviously, because it's already on YouTube. Yeah, so that's kind of it. I will think about, like, I'll probably want to submit the code that we have written today to the repository, because I mean it's like way faster, so it will make my debugging experience in Visual Studio less miserable. I might need to clean the code up a bit because I was a bit rushed towards the end because I just wanted to like get it done, get it run. I might add an operator to just not to like reduce the visual noise of these .data things. Maybe that'll make things a bit slower, but not much. And yeah, that'll be good. I'm slightly disappointed by the fact that we didn't seem to get any performance back in like, oh, this is not libc++, this is libstd.c++. Alright, while I'm waiting a couple minutes for the questions, let me just build this with libstd.c++. Alright, what am I doing? What do I want? Oh, right, yeah, so I want to make file. I don't know even. Oh, is libc++ just the default in Clang now? I don't think so. Or maybe it is. It might be. Let's see. How do I know this? Yeah, I don't think it's the default, but I'm not sure. Command line. Let's see. But maybe it is. It might be. Let's see. Alright, yeah, so you need to do like this thing. Come on. Right. So this will only work with Clang. Okay. So basically libc++ isn't really installed on my system properly or something like this. Is this like an apt thing? Oh no! 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 This was not a regex! No! Okay. Alright. I don't know how to do this. I suspect Clang is not using libc++. So that's not great, because I don't have a comparison point against libc++. I only have it against libstd.c++. Let's look at libstd.c++ vector. Alright. But again, so yeah, thank you everybody for being on the stream. Hopefully this was fun. And I will post on Twitter when we will do this again and what this stream will be about and stuff. And I will not look at libc++ source code because it's too late already. Good night everyone. Thank you.